In the previous video, I tried to recreate the Death Stranding's Terrain Scan effect. While I thought I nailed it, a lot of you pointed out that there's one crucial thing I missed. Those tiny yet essential indicators that appear above the terrain. Eager to rinse the shame off my face, I jumped headfirst into the challenge. What I initially thought would be a quick fix turned into a 3-week-long journey that showed me just how complex and detailed this effect really is. But hold on, I can't just show it to you. We need to go back where we left off in order to truly appreciate this effect. However, before we start, I need to address the mistake I made in the first part of the video. As it was correctly pointed out by the Maz, the lines are looking quite jaggedy and aliased. This can be especially visible at specific angles. I explored the issue a bit and tried out different solutions before realizing something. I messed up pixel sampling of the Sobel outline effect. I specified the vertical offset incorrectly, which caused the outline effect only to check the distances between the horizontal pixels, instead of checking both the vertical and the horizontal ones. Oops. With that fixed, the lines look so much better. With that out of the way, I started analyzing the indicators. The first thing I noticed about this effect is that the indicators are being distributed in some kind of a grid pattern. The grid is aligned with the direction of the terrain scan effect, and it consists of 75 rows and 140 columns. I mean, it's an approximation. I definitely didn't enter photo mode and count them manually. The indicators inside the grid are offset above the ground and follow the general shape of the terrain. Of course, there's a lot more we could dissect here, but this seems like the core of the effect, so let's start with this. The first idea that popped into my head was to calculate the position of each indicator in the grid, raise the whole grid up, and then cast a ray downwards to check where it collides with the terrain. Then I could apply a vertical offset to the indicator so that it would appear above the terrain. I wrote this little code snippet that distributes objects into a grid. It all appears to be working nicely, at least if you're fine with losing all your frame rate and locking the game at 30 FPS. Since I'm recreating an effect from Death Stranding and not from Starfield, this performance is not acceptable, so I need to address this. There are two performance-heavy parts here. First up, the CPU has a tough time calculating the positions of 10,000 indicators. And then there's the GPU, which would definitely prefer to receive one clear instruction to draw 10,000 objects instead of being asked 10,000 times to draw something. The camera frustum calling is reducing this number a bit, but it's not enough. Let's make it easier for them. An ideal solution would be to offload everything to the GPU. The CPU would just tell the GPU the number of indicators that need to be drawn, and the GPU would take care of the rest. Fortunately, we can do just that with the fantastic capabilities of compute shaders and indirect rendering. First, I implemented a compute shader that calculates the position of each indicator and stores it in a special graphics buffer. This buffer is then used by the rendering shader to draw the indicator at the correct position. Finally, on the CPU side, all we need to do is tell everyone how many indicators need to be calculated and rendered. Great. Let's see how this looks. Well, there's good news and bad news. The good news is that performance-wise, we're looking really good. However, the bad news is that there are no visible indicators now. What is going on? It turns out that when you're using an indirect drawing approach, you're supposed to manually specify the bounding box of the mesh so that the rendering pipeline knows when the mesh is outside of the camera view. Normally, this is done automatically by the camera, but with indirect rendering, we need to do this manually. There we go. We can see the indicators again. And let's take a look at the performance now. There is a small drop from 170 FPS to around 160 FPS, but this is much better than the 30 FPS we had before. Well, this was quite the effort just to get the indicators rendered efficiently. However, I can't just leave them floating in the air. They need to follow the shape of the terrain. At first, I thought it would be a good idea to shoot a ray for each indicator and check how it collides with the terrain. However, since the indicators live completely on the GPU now, this idea suddenly seemed too complicated because Unity's physics engine lives on the CPU, and I don't have access to it on the GPU. After investigating different techniques, I noticed that Unity first renders terrain normals and depth into a special texture. This texture can then be used for different effects. This inspired me and I came up with this hacky solution. I will add another camera vertically above the indicators and use it to render terrain depth into a separate texture. Since the camera is orthographic and perfectly encapsulates indicators, I can use the position of each indicator as a texture sampling coordinate for the depth texture. This sample depth can then be used as the distance of the indicator from the camera. So let's see all of this in action. First, I start the terrain scan from a certain location. Then, based on the location of the scan and the horizontal area that the indicators will take, I position an orthographic camera vertically above that area and adjust its field of view to encapsulate the area of the indicators perfectly. Then, I render only the depth of the terrain for this camera into a separate texture. Finally, I provide this depth texture to a compute shader that can use it as a distance map to calculate the distance of each indicator from the camera. And here are the results. The indicators are perfectly positioned on the surface of the terrain. Also, since this depth texture is already on the GPU, the compute shader can access it super fast. So, if you have a bottle of champagne somewhere near you, this would be the time to pop it open. And you may be thinking, we do have to pay the cost of rendering the terrain one additional time. That's true, but I have to say I'm okay with it since we render a very small part of the terrain and we only do this for one frame at the start of the effect. The result is stored in a texture that we can reuse throughout the duration of the scan. So, we're positioning the indicators correctly, but what about their rotation? I quickly booted the game and ran around the indicators a bit. It turns out they always face towards the camera so that they're always visible. I implemented this billboarding logic inside the rendering shader by having a look at Unity's source code for the Quaternion class. All I had to do was rewrite the C# code into an HLSL code. There we go. The indicators are looking at the camera now at all times. What? It turns out I messed up the indexing of a rotation matrix while rewriting the HLSL code. Basically, I swapped the rows with columns. Oops. Like I was saying, the indicators are looking at the camera now at all times. Awesome. Also, let's quickly disable the ones that are outside the max visible angle for the terrain scan effect. We've already implemented logic for that in the first video, so I won't go into more details here. With that out of the way, let's give them a proper shape and color. By looking at the manual, we can see that the shape of the indicator determines the type of surface beneath it, while the color of the indicator determines the danger. Walkable surfaces are blue, dangerous are yellow, while the red indicators determine surfaces that will cause the player to fall. Additionally, there are some special surfaces like tall grass or slippery rocks that have special indicators and colors. Armed with that knowledge, I implemented a shader that samples the shape of the indicator from one texture and the color from another. This way, with a bit of math, I can specify the part of the texture that the indicator should sample in order to visualize the correct shape and color. This is a common rendering technique used to reduce the amount of required textures that the GPU needs to swap between in order to render an object. While the shader is sorted out, I still don't know which type of surface is beneath each indicator, so I don't know which shape and color should each indicator have. Based on the manual from Death Stranding, the default walkable terrain indicator is a small blue rectangle. When the terrain gets steeper, it becomes yellow before it finally turns red when the terrain can't be traversed. To determine the steepness of the surface, I will need the normal vector of the terrain. So, alongside the depth texture, I now output the terrain normal vectors into another texture. Then, in the compute shader, I can sample this normal texture for each indicator to obtain the normal vector. Then, I can compare the direction of this normal vector with the world up vector. This tells me the angle of the surface, which I can use to determine which type of terrain this indicator represents. Let's see how this looks. On a flat surface, all indicators are blue squares, representing a fully walkable surface. But if I now test the effect on this steep part of the terrain, they should change the color. Wait, this doesn't seem right. Why do the indicators remain blue on this steep part of the terrain? Well, I've traced the code 3 or 4 times already and everything seems correct. I need a better insight into what is going on here. I quickly created this helper compute shader that samples the normal texture and outputs the normal vector into a buffer that I can then read on the CPU and visualize in the scene. So let's see how the normals look in this case. This doesn't seem right. Let's try this again. Okay, this looks better. This is what is causing the issue. The normal vectors are pointing upwards, even though the surface is very steep. Maybe the terrain rendering shader is incorrectly writing normal vectors? Well, after 3 long hours of testing different parts of the code, I concluded that everything was actually working correctly. The only mistake I made in the process is that I've set the texture to be of type 8-bit unorm. This means that each texture channel is saved as an unsigned value between 0 and 1. Of course, this contradicts the fact that the normal vector can have values in the range between -1 and 1. After changing the texture type from unorm to snorm, normals finally started looking as expected. And if I now test the look of the indicators on this steep terrain, they should all be colored correctly. Yes, finally, everything is working as expected. At least for the basic terrain type. If, for example, I test the scan effect above water, it wonderfully syncs. Kinda like the chances of me ever finalizing this effect. Luckily, handling water should be relatively simple. In this environment, the water level is global for the whole scene and the water surface is relatively still, without any big waves. This means that in order to determine if the indicator represents a water surface, I can just check if the terrain height of the indicator is below the water height. If it is, I just need to switch the indicator type to represent a water surface and offset it vertically above the surface. Easy, right? I can also use this terrain height to determine the distance from the water surface level, or in other words, the depth of the water. Then, based on this water depth, I can switch between different water indicators. And let's see this in action. The indicators show a steep terrain surface until they reach the water. Then they change to an indicator type of the water and change color based on the depth. Awesome. Finally, something that worked immediately on the first try. The last thing regarding the shape and color of the indicators is to handle these special cases of terrain like grass, concrete or slippery rocks. For them, there is no straightforward way to know which special type of terrain is currently beneath the indicator. I need to provide this information manually. To do that, I created these special objects that are invisible to the camera. They're on a special layer and contain a shader that only writes their ID to the output texture. This ID is an indicator that specifies which type of terrain this special object represents. For example, for this along a grass section, I will place a special invisible object around the grass. Then, after rendering the depth and normals of the terrain, I will render this special object into another texture that only holds the IDs of the terrain surface. Actually, there is one optimization trick we could do here. Since we're currently using only 3 out of 4 channels in the normals texture, we can write the ID of special objects into the alpha channel of the normals texture instead of using another texture for only IDs. Pretty neat, right? Then, in the compute shader, when we sample the normal texture, alongside the normal vector, we get the ID of the surface for free, all with one texture sample. Finally, we can now use this ID to change the shape and color of the indicator according to the surface type. Let's see this in action. Above this tall grass patch, we can now see green indicators representing this special terrain type. And above this slippery rock surface, a special danger indicator appears. Awesome. Our indicators are starting to shape up pretty nicely, but they're still not complete. Let's check out the original effect to see what we can improve next. The first and most noticeable thing is that the indicators appear immediately, but are constricted to the range of the terrain scan effect. After that, they have this constant fading animation that appears to be offset based on the indicator's distance from the origin of the effect. The fading animation plays exactly 6 times before the indicator completely disappears. Apart from the opacity animation, the indicators are also constantly moving up and down. At first, I thought they were all moving without any offset, but after inspecting indicators in this closed-up environment, it became clear that the vertical movement also has an offset that is probably also applied based on the distance from the origin of the effect. Let's tackle the movement first, since it turned out pretty simple. The vertical movement is a result of applying a sine wave offset to the height of the indicator. To see this more clearly, I've increased the offset and amplitude amount to emphasize their visibility. And this is how it looks with values more tuned in to match the original effect. After setting the movement, I started to tackle the visibility animation. And to be honest, it took quite a few iterations to get it to a state I was content with. Though it doesn't require any special technique or an idea to execute, it took quite a bit of tweaking to get it to a somewhat decent state. And I think it looks pretty nice. With that, the indicators seem almost complete. They're correctly spawning, moving and flickering. However, there's one more thing I've ignored so far: the special behavior of red indicators. So let's analyze them first. When they first appear, they're overlaid with this glowing red shape to give the illusion that they're shining really bright. This is super important since it shifts the player's focus towards them. This glowing red shape remains visible for a very short duration before being reduced in size and converted to this X-shape indicator. The indicator remains visible the whole time and is unaffected by the visibility animation of other indicators. Finally, at the end of the scan effect, the indicators fade out just like every other indicator. Now, let's examine them in a bit more detail. First, it's worth noticing that the red indicators appear a bit sooner than the others. They even appear before the terrain scan front line reaches them. Also, they seem to be flickering throughout their lifetime. Although this doesn't always happen, so I'm unsure if this is an intentional effect or a rendering issue. That's why I decided not to implement it. Let me know what you think. Is the flickering intentional? Anyhow, let's start with the glowing red shape. For this, I created this texture using radial and reflected gradients in Photoshop. Back in Unity, I had the idea of using the same object to show the red glow and the X-shaped indicator by animating its size. As the indicator shrinks down, I will slowly show the X shape instead of the glowing shape. However, when I enlarged the whole indicator, the X shape also stretched. This is of course an expected behavior, but I have to say that I completely overlooked the fact that it would happen. Anyhow, after a bit of math and a couple of failed iterations, I've managed to implement a multiplier for the UV coordinates that will keep them from stretching during the resize of the indicator. Also, since I want the glowing shape to be fully stretched, I apply this multiplier only to the X shape. And this is how it looks when implemented in the final effect. I think it turned out pretty close to the original effect. What do you think? Once I tested the entire effect under various conditions, I returned to playing the game to make sure I had thoroughly explored every detail of the terrain scan effect before wrapping up this adventure. At first, I was really excited, but that feeling soon changed when I discovered that the terrain scan effect made the footsteps glow, revealing the player's tracks in a really cool way. Contrary to the indicators, the footsteps appear immediately when the effect starts. The terrain scan front line doesn't need to reach them. Also, while the effect is active, any new footsteps left in the area of the effect will automatically get highlighted. However, if you leave any footsteps outside of the terrain scan area, they won't be highlighted. Finally, they remain highlighted even when the indicators disappear. They slowly transition from a highlighted state to a normal one over time. However, If you try to leave any new footsteps in the area of those highlighted footsteps, they won't be highlighted since the terrain scan effect has expired. Finally, let's have a look at the highlight effect itself. It seems to be a bright, squarish texture applied over the screen, but only visible on the footsteps. If you're wondering why I got this idea, it's because the squares don't follow the shape of the footstep when I rotate the camera. They remain parallel with the screen boundaries. To implement this whole footstep system, I will need to do quite a lot of stuff. First, I need to bring Adam to life. Currently, I can't control him at all. He's just stuck in this static pose. So I downloaded this third-person controller package from Unity and replaced the default mannequin with Adam. He embraced it pretty well, despite his legs being a bit wobbly. Next, to leave a footstep when his feet touch the ground, I added these small sphere colliders that will check for collision with the terrain and leave a footstep at the position of impact. However, this calculation was not precise enough, resulting in the footstep rotation not matching the terrain. To correct that, when the spheres detect the collision with the terrain, I shoot an additional small ray downwards to get the exact position and orientation of the terrain surface at the point of impact, which I then apply to the footstep. This turned out pretty nice, but the footsteps are still just small white planes. To make them look like Adam's footprint, I jumped in Blender and cut out Adam's feet. But don't worry, he didn't feel a thing. Finally, I imported the feet back into Unity. Then I set up the camera directly below them and rendered them into a small texture. Now I can use this texture to show an appropriate footstep instead of white planes. Since the footstep placement system appears to be working fine now... Wait, what? Like I was saying, since the footstep placement system appears to be working fine now, I focused on the highlight shader. Initially, I thought that I would need to create a special texture for this effect, but it turned out that I could just use the screen UV coordinates and tile them a lot. Then, by using the minimum of the tiled X and Y coordinate, I could achieve this sort of interesting squarish pattern that is very similar to the original effect. If I multiply everything with a bright blue color, it should look pretty close to the original. I was pretty happy with how this looked, especially with the fact that I managed to avoid an additional texture sample. Sweet. And let's see everything in action. First, Adam leaves normal footsteps while walking on the terrain. Then, when the terrain scan is activated, only the footsteps inside the scan area get immediately highlighted and remain highlighted during the whole length of the scan. Any new footstep will get highlighted as well, and footsteps outside the scan area will remain normal. Finally, after the effect expires, the footsteps slowly lose their highlight. Nice. This whole footstep system added an additional 2 days of work to this experiment, but I think it was worth it. Especially to include it as the final piece of the effect. I mean, this is the final piece of the effect, right? Right? It is, right? Well, it turned out there is one more special part of the effect I managed to overlook this whole time. When the terrain scan is cast near special interactable objects, they glow with this pink outline and flicker a bit. The flickering is faster than the visibility animation of the indicators and doesn't seem to be connected in any way. After a couple of seconds, the flickering stops and the outline disappears. This effect is important since it provides the player with information about these special interactable objects that he can use to replenish health or support broken shoes. Even though the experiment got a bit too large already, I decided to implement this as well since it's a vital gameplay part of the effect. Fortunately, I've already researched the different outline effects for the terrain scan lines in the first video. This Sobel outline filter seemed perfect for this use case. I've added an additional render pass that renders only these special objects with a shader that implements this Sobel outline filter for both the differences in depth and normals of the objects. Since I don't have any bug models to use for demonstration, I've set up this small floating rock sample that should serve the point. And let's see it in action. The rocks start glowing with a pink outline and flicker a bit before the outline fades out. Nice, right? Wow, this was quite a journey, wasn't it? Let's see everything combined, shall we? Well, I have to say I'm pretty happy I managed to recreate everything. If you saw something I overlooked or missed, please let me know in the comment section. If you enjoyed being a part of this exploration with me and would like to join me on the next one, make sure to subscribe. Thank you for your time and see you in the next one.